What if I told you the universe isn't actually expanding?
Oh, that's a bold way to start.
I mean, what if mathematically speaking, the exact same astronomical observations we record every single night can be explained by a completely static, unchanging universe?
Yeah.
Like where every atom, every planet, and every ruler we use to measure distance is just steadily shrinking over time.
It sounds like a pure provocation,
Yeah.
but it is actually a perfectly valid, rigorous mathematical duality. We cling to this idea of expanding space because it appeals to our macroscopic intuition.
Right? Our everyday experience.
Exactly. But the deeper we look at the differential geometry, the more those rigid intuitions just sort of dissolve into something much more fluid and arguably much more beautiful.
Welcome to this custom-tailored deep dive. You, our listener, have provided an absolutely incredible, dense stack of sources for us today.
Yeah, you really didn't hold back.
Not at all. We are looking at deep-in-the-weeds academic papers on cosmological metrics. We've got the Bunn and Hogg paper on kinematic redshift, the Price and Romano paper on bound systems, plus these really intense astrophysics debates scraped from Stack Exchange.
And some highly detailed cosmological lectures, too.
So, we are dispensing with the middle school explanations today. We know you're already well-versed in the basics. Our mission here is to gently but rigorously unravel the true mechanics of cosmic expansion.
Without the anxiety of information overload.
Exactly. We want to strip away the flawed analogies that plague even university-level textbooks.
We're basically going to look under the hood of the Friedman-Lemaitre-Robertson-Walker metric. We're going to talk about parallel transport, the illusion of the expanding rubber sheet, and the actual tensor-level reality of what happens to the cosmos as time ticks forward.
And as we settle into this unhurried, ambient exploration, taking a slow breath to prepare for some truly cosmic scales, I want to gently recommend a perfect companion for this kind of deep, late-night contemplation.
Oh yeah, the YouTube channel.
Right. It's called Decoding the Dark. If you find yourself captivated by these quiet mysteries of the universe, you should definitely subscribe and like their video. It's just a brilliant, soothing resource for letting the sheer scale of the cosmos wash over you. So settle in, get comfortable. Okay, let's unpack this.
So to build an accurate model of the universe, we first have to demolish a geometric prejudice that is hardwired into the human brain.
Meaning our need for boundaries.
Yeah, exactly. We are evolved to understand embedded objects. If a balloon expands, it expands into the air of a room. If a physical volume grows, our brains tell us it requires a higher dimensional boundary to grow into.
Right, which makes the classic balloon analogy really confusing.
When people look at that classic balloon analogy for the expanding universe, they immediately trip over this cognitive bias. They demand to know what the 3D room is that the 2D balloon is expanding into.
Which is funny because the sources from the physics forums are absolutely ruthless about tearing that analogy apart for this exact reason.
Oh, they hate it.
They really do. Because in differential geometry, we're dealing with manifolds. And thanks to things like the Whitney embedding theorem, we know that while you can mathematically embed a manifold into a higher dimensional space, there's absolutely no physical or mathematical requirement to actually do so.
Right. The manifold is completely self-contained. The curvature is intrinsic.
Intrinsic being the key word there.
Intrinsic is definitely the key word. A manifold contains its own metric. It has its own set of rules for determining the distance between 2 points. So to ask what the universe is expanding into is, it's basically attempting to assign a coordinate system outside of the manifold.
Which is impossible, right? Because the manifold is all there is.
By definition, yeah. The expansion is simply a time-dependent evolution of the metric itself. The distance between internal coordinates is increasing, governed by a global scale factor.
So there is no edge?
No edge, no boundary, and no outer void. If the universe is infinite, it was infinitely dense at the initial singularity, and it is infinite now.
Which brings us directly into the mathematical engine of standard cosmology, the FLRW metric.
The Friedman-Lemaitre-Robertson-Walker metric.
Right, so we accept the cosmological principle that the universe is homogeneous and isotropic on the largest scales. It's this uniform, idealized fluid. But the metric forces us to split our concept of distance into two entirely separate ideas.
Yeah, co-moving distance and proper distance.
Let's break those down.
Okay, so the co-moving distance is essentially the coordinate grid. Imagine a vast three-dimensional lattice. If we ignore local peculiar velocities for a moment, The galaxies just sit motionless at the intersections of this lattice.
So their cosmic address never changes.
Right, their address never changes. The co-moving distance between the Milky Way and a distant quasar is a constant value.
But the proper distance is different. That's the actual physical distance you'd measure if you could, like, freeze time and lay a massively long tape measure from here to that quasar.
Yes, and that proper distance is constantly increasing. That divergence between the coordinate distance and the physical distance is driven entirely by the scale factor.
Which is usually denoted as of t.
Right. The scale factor is a dimensionless function of time. It acts as a universal multiplier for the spatial part of the metric tensor. So the physical proper distance is simply the co-moving coordinate distance multiplied by the scale factor at that specific moment in cosmic time.
The sources provide a purely mathematical analogy for this that I love, because it elegantly removes the whole physical stretching fabric idea completely.
Oh, the integers.
Yeah, the infinite set of integers. So consider an infinite set of integers, 1, 2, 3, 4, on out to infinity.
Okay.
If I apply a scale factor of 2, the set becomes 2, 4, 6, 8. The distance between the numbers is doubled, but the infinite set didn't expand into anything.
Right, you didn't have to add more numbers to the end.
Because there is no end. The cardinality of the set is identical. The spacing just changed as a fundamental property of the mathematical rule applied to it.
And importantly, in that integer analogy, no single number was the center of the multiplication.
Oh, right, because 2 went to 4 and 4 went to 8.
Exactly. Because the spatial slices of the FLRW metric are maximally symmetric, every point is perfectly unspecial. Every observer at every node on that coordinate grid perceives the exact same isotropic increase in proper distance away from themselves.
But this is exactly where the deepest friction in your sources lies. Specifically in that fiercely debated paper, Expanding Space, the root of all evil.
Yeah, by Francis, Barnes, James, and Lewis, that paper caused quite a stir.
Because physicists look at the scale factor A of t, and they split into two warring camps on how to interpret it ontologically. The dominant pop science camp says that the scale factor represents the physical fabric of space stretching.
Treating space as a substantive material.
Exactly, like a rubber sheet that gets pulled taut, dragging the galaxies along for the ride.
And the authors of that paper, along with a lot of people in the rigorous relativity community, refer to this as the fallacy of reifying the rubber sheet.
Reifying, making an abstract concept real.
Right. It's the dangerous habit of taking an abstract metric coefficient and treating it as a tangible fluid with physical properties, like tensile strength or kinematic friction. Space does not have a physical structure that can grip a galaxy and pull it.
But this reification is what leads to the standard textbook explanation for cosmological redshift.
The tired light and stretched wave ideas.
Yeah, the classic explanation is that a photon is emitted from a distant galaxy, and as it travels toward us for billions of years, the literal fabric of space stretches out beneath it, catching the light wave and physically stretching its wavelength into the red end of the spectrum.
But if space isn't a physical fabric, that explanation completely falls apart.
It does. And this is where the paper by Bunn and Hogg, The Kinematic Origin of the Cosmological Redshift, offers a mathematically pristine alternative.
They argue that invoking a mystical stretching spacetime is completely unnecessary.
Thank goodness.
Right. General relativity dictates that spacetime is a pseudo-Riemannian manifold. This means that at any point and along any path, you can define a locally flat Minkowskian spacetime.
Wait, so when I hear an ambulance drive by and the pitch drops, that's a Doppler shift. Are you saying the redshift of galaxies is essentially the exact same thing, just accumulated over billions of light years?
That is exactly what they're saying. Under general relativity, the expansion is, at its core, galaxies just moving apart. Treating space as a physical river that carries galaxies away leads to terrible misconceptions.
But if we adopt the Bunn and Hogg framework, we immediately hit a wall with superluminal recession, don't we?
Ah, yes. The speed limit of the universe.
Right. Special relativity strictly forbids local motion faster than the speed of light. So if we treat cosmological redshift as purely kinematic Doppler shifts, like ambulances driving down the street, how do we mathematically reconcile the fact that distant galaxies are receding from us at like 3 times the speed of light without breaking Lorentz invariance?
That is the crucial counterargument. But differential geometry actually provides the solution here via parallel transport.
Okay, walk me through that.
Bunn and Hogg aren't saying the distant galaxy is moving through our local inertial frame at 3 times the speed of light. They are analyzing the photon's journey by breaking it down into an infinite series of infinitesimally small, overlapping inertial frames lining the path from the emitter to the observer.
Ah, so we are looking at the tangent space at every single point along the photon's geodesic.
Precisely. Imagine a chain of observers stationed along the photon's path. Each observer is moving at a minuscule, non-relativistic velocity relative to their immediate neighbor.
Okay, I'm picturing it.
As the photon passes from the first observer to the second, it undergoes a tiny, purely kinematic, special relativistic Doppler shift. Then it passes to the third observer, undergoing another tiny kinematic shift.
So we mathematically parallel transport the velocity vector of the source along the light cone to the observer.
Yes, exactly. When you integrate these infinitesimal kinematic Doppler shifts across the entire geodesic from the emitter to the receiver, the resulting accumulated shift perfectly matches the cosmological redshift derived from the FLRW scale factor.
Oh, wow.
The beauty of this is that it preserves the local physics. Light doesn't need to know that the global universe is expanding. It only interacts with its immediate, flat space-time neighborhood.
The redshift is fundamentally just a sequence of local kinematic Doppler shifts between freely falling observers
Yes.
that drastically changes how we picture the universe. It isn't a river of fabric stretching and distorting the light. It is just a massive collection of objects drifting apart in local inertial frames.
It's a much more elegant way to look at it, mathematically speaking.
Before we push this kinematic reality into what happens to bound systems, like our own solar system, I want to take a brief, relaxing pause.
Always a good idea.
If you are deeply enjoying this untangling of cosmic mechanics, I gently urge you to check out the YouTube channel Decoding the Dark. Subscribe and like their video and let their unhurried, visually stunning explorations of the dark universe be a companion for your quietest, most curious nights.
It really is a great channel for this sort of mood.
Absolutely. So, if we completely discard the rubber sheet and accept that expansion is just a metric evolution, a kinematic drifting apart, we have to confront a massive misunderstanding about local physics.
The tug-of-war myth.
Yes, there is a very common narrative that the expansion of the universe is gently tugging on everything. Tugging on our galaxy, on our solar system, on the atomic bonds in your coffee cup.
Right, the idea is that space is trying to expand your body, but your electromagnetic forces are acting like a bungee cord, fighting back and holding you together.
It is an incredibly pervasive myth, suggesting a constant localized tug-of-war between the FLRW expansion and the fundamental forces.
But it is fundamentally incorrect. The paper you provided by Price and Romano, in an expanding universe, what doesn't expand, mathematically eradicates this idea entirely.
Let's get into the mechanics of their proof. Because they didn't just philosophize about it, they put a classical bound system, analogous to a hydrogen atom governed by an inverse square force law, directly into the expanding metric to see what the Lagrangian mechanics would actually do.
And the results were definitive. They demonstrated that a bound system does not experience a continuous, weak outward pull. Instead, the dynamics are entirely all or nothing.
All or nothing.
Right. When you place a bound system into a cosmological background that is expanding, there is an incredibly brief, transient period where the system adjusts to the initial condition.
A transient phase, meaning the atom might shudder or oscillate very briefly.
Exactly. The atomic orbit might slightly shift its radius based on the specific initial state of the background metric. But once that microscopic transient phase decays, the system completely decouples from the cosmic expansion.
It just ignores it.
Completely. The proper distance between the electron and the nucleus becomes utterly constant. It perfectly, perpetually ignores the scale factor A of T.
I think there was an analogy in the sources about an ant in a house, right?
Yeah, that's a great way to visualize it. Dark energy or expansion acting on a solar system is like an ant pushing on a house. The ant exerts a force, sure, but it fundamentally does not change the house's position because the house's binding friction is immensely stronger.
This is where we need to abandon the physical analogies and talk about the metric tensors themselves. The reason the solar system or an atom doesn't expand isn't because a local force is overpowering the expansion of space. It's because in a localized, gravitationally bound area, the FLRW metric is simply no longer the correct description of spacetime.
That is the core of the issue. The FLRW metric requires a perfectly homogeneous fluid of matter and energy, but the universe is not homogeneous on small scales.
No, it's very clumpy.
Right. The mass of our sun creates a deep local gravitational well. The geometry of space-time in our solar system is not governed by the expanding FLRW metric. It is governed, to a very good approximation, by the static Schwarzschild metric, or a slightly perturbed Kerr metric if we account for spin.
So the expansion doesn't try to pull and fail. The geometry of expansion literally ceases to exist in the presence of overwhelming local mass density. Our local space-time is not expanding.
What's fascinating here is how this mathematical reality resolves one of the most counterintuitive thought experiments in standard cosmology.
Oh, the tethered galaxy problem.
Yes.
I want to spend some time on this, because this is where the kinematic interpretation really flexes its muscles over the rubber sheet illusion. Let's set up the boundary conditions for the listener.
Okay, picture this.
We imagine a magical, unbreakable, massless cable. We attach one end to the Milky Way, and we spool it out millions of light years across the intergalactic void and tether it to a distant galaxy that is currently receding from us with the Hubble flow.
By doing this, we have artificially forced this distant galaxy to maintain a constant proper distance from us. We have violently pulled it out of its co-moving coordinate frame. Its recession velocity relative to us is now exactly 0.
Now the thought experiment. We take a pair of cosmic scissors and we sever the tether. What happens to that distant galaxy?
The textbook rubber sheet intuition says that because space is a flowing river, the moment you cut the rope, the galaxy will get caught in the current of expanding space and immediately be swept away, resuming its recession.
But the equations of general relativity, specifically the Friedmann equations, evaluating the deceleration parameter in a matter-dominated universe, dictate the exact opposite.
Yeah. When you sever the tether, the galaxy doesn't fly away, it falls toward us.
It falls inward. The universe is expanding everywhere, but this untethered galaxy falls toward the Milky Way. Walk us through the specific gravitational mechanics of why that happens.
Well, if we strip away the illusion of the stretching rubber sheet, what are we left with? We have two massive objects with a relative velocity of 0. Between them lies a vast expanse of space-time containing a certain density of matter, gas, dark matter, stray photons. According to Geiss's law for gravity, or Birkhoff's theorem in relativity, the gravitational dynamics between these two stationary objects are dictated by the mass enclosed within a sphere drawn between them.
Since they are stationary relative to each other, the only force acting on the distant galaxy at the exact moment the tether is cut is the gravitational attraction of the Milky Way and all that mass in the space between us.
Precisely. There is no mystical expansion force pushing it outward because expansion is fundamentally a statement about inertia.
Right, the initial kick.
Yeah, the Big Bang imparted an initial outward momentum to the co-moving coordinate grid. If you manually stop a galaxy, you have removed that initial inertia. It is now just a heavy object in a gravitational field, so it accelerates toward the center of mass. It falls inward.
Now, to be perfectly rigorous, we have to acknowledge dark energy here, the cosmological constant, lambda.
Yes, that changes things slightly at massive scales.
If the tethered galaxy is far enough away, the repulsive effect of dark energy, which scales with distance, might overwhelm the gravitational attraction of the enclosed mass.
Right.
In that specific case, it would accelerate away, but not because of a flowing river of space.
Right. It would accelerate away because dark energy exerts a localized repulsive pressure.
A vital distinction. But in a pure matter-dominated universe, or at distances where gravity still dominates lambda, that tethered galaxy is plunging straight toward us. It completely shatters the physical fabric illusion.
It really does. It's a beautiful way to show how misleading our initial intuitions can be.
But here's the problem with the FLRW metric we've just spent so much time praising. It requires this perfectly smooth, idealized universe. But look out the window. Look at the cosmic web. The universe isn't a smooth fluid. It is violently clumpy.
Very true.
We have incredibly dense galaxy clusters surrounded by unimaginably vast empty voids. How does the mathematics of expansion survive in a universe that looks like Swiss cheese?
This is a highly active area of cosmological modeling. You are referring to the Swiss cheese models of the universe, which often utilize the Dyer-Roeder approximation and the concept of Kotler holes, also known as Einstein-Strauss vacuums.
Let's break down the mechanics of a Kotler hole, because it fundamentally alters how light propagates through the universe.
Okay, so in the Swiss cheese model, theorists take the idealized, expanding FLRW fluid and mathematically carve out spherical holes in it.
Like literal bubbles in the...
Yeah, exactly. They take all the mass that would have been evenly distributed inside that sphere, and they compress it into a single, highly dense central object, like a galaxy cluster.
So inside the boundary of this spherical hole, it is essentially a perfect vacuum, save for the massive object in the dead center.
Yes. And the critical boundary condition here is that you must perfectly match the internal static geometry of the hole with the external expanding geometry of the FLRW fluid at the boundary layer. Inside the Kotler hole, the geometry is completely static. It is a Schwarzschild or Schwarzschild de Sitter metric. The space-time inside the void is not expanding.
This blew my mind when I went through the source materials. If a photon from a quasar billions of light years away is traveling toward my telescope, and its geodesic happens to cross through one of these massive Kotler holes, while the photon is inside the void, the space it is traveling through isn't expanding.
Correct. As the photon crosses the boundary from the FLRW cheese into the Kotler hole, it ceases to experience metric expansion.
Wow.
It travels through static space-time, experiencing only the localized gravitational lensing and the Sachs-Wolf effect from the central mass's potential well. It only resumes experiencing expansion once it exits the hole and re-enters the FLRW fluid.
Which means our measurements of the universe, our calculations of distance based on redshift and luminosity are incredibly sensitive to the exact path the light took.
Extremely sensitive.
If light travels through mostly empty voids, the Dyer-Roeder approximation requires us to adjust the density parameter omega along that specific line of sight. The photon hasn't experienced the same amount of expansion as a photon that traveled through the average density of the universe.
It reveals how the FLRW metric, while magnificent on the largest scales, is a gross simplification of the granular, localized reality of spacetime. We are observing the universe through a complex, refracting, static, and expanding mosaic.
And observing that mosaic brings up the question of the global shape of the manifold itself. Cosmic topology.
Ah, topology. That's where things get really weird.
The sources note that the Planck satellite data suggests our observable universe is spatially flat. The density parameter omega is indistinguishable from 1. The angles of a cosmic scale triangle add up to exactly 180 degrees. Most people assume that means the universe is infinite.
It's a natural assumption.
But the astrophysicist Joseph Silk, in the interview transcript you provided, points out a crucial loophole.
Local geometry does not dictate global topology.
Right. Tell us about that.
Think of a perfectly flat sheet of paper. You can roll it into a cylinder. The intrinsic geometry on the surface of the cylinder remains perfectly flat. You haven't distorted any local distances, but you have fundamentally changed its global topology. It is now finite and multiply connected in one dimension.
And if we extrapolate that topological trick into 3 dimensions, we get the 3 torus, the donut universe. It is spatially flat, yet finite.
In a 3 torus topology, there are no edges and no boundaries. If you launch a spacecraft in a straight line and wait long enough, it will not hit a wall. It will eventually return to its exact starting point, having circumnavigated the finite volume of the universe.
It's the video game boundary effect, like the old Asteroids arcade game. You fly off the right side of the screen and instantly reappear on the left side with no interruption in your momentum.
Exactly like asteroids.
But this creates an incredible observational paradox. Because light doesn't just stop, it keeps wrapping around.
Exactly. In a multiply-connected universe, light can take multiple paths to reach the same observer. There is a direct short path, but there's also a longer path wrapping entirely around the universe. If the universe's total volume is small enough relative to the speed of light and the age of the cosmos, we should be able to see ghosts of the same astronomical objects.
So we could point a telescope into deep space, capture an image of a quasar, and then turn the telescope 180 degrees in the exact opposite direction and see the exact same quasar, just millions of years older or younger, depending on the travel time of the light that took the long way around the torus.
Yes. Joseph Silk noted that we could theoretically see the back of our own Milky Way galaxy from billions of years ago.
But the WMAP and Planck data effectively killed this theory, right? If the universe wrapped around itself, we would see topological lensing. The cosmic microwave background would show repeating patterns, like cosmic wallpaper, where the spheres of our observable horizon intersect with themselves.
Well, it killed specific small volume models. Cosmologists extensively searched the CMB data for circles in the sky, matched temperature fluctuations that would prove the universe intersects with itself.
Like the dodecahedral shape.
Yeah, the search for the Poincare dodecahedral space. It's a beautifully complex 12-sided spherical topology. It was highly anticipated. But the data yielded no statistically significant matching circles.
So the universe doesn't wrap around.
We must be precise here. We found no evidence of a multiply connected topology at a scale smaller than our observable horizon.
Ah,
If the fundamental domain of a torus universe is significantly larger than the 46 billion light-year radius we can observe, the light hasn't had time to wrap around yet. The topological signatures would be hidden beyond our particle horizon. The possibility of a finite, multiply connected universe remains a perfectly valid mathematical hypothesis.
we've built an incredibly rigorous model of metric expansion so far. We've replaced the rubber sheet with kinematic parallel transport. We've navigated static Kotler holes and mapped out toroidal topologies. But if the listener really wants to sit back and experience the absolute fluidity of modern physics, we have to look at the alternative dualities in the source material.
Oh, the dualities, yes.
Because mathematics allows us to describe the exact same physical observations using entirely different conceptual frameworks.
This touches on the principle of conformal transformations. In physics, we often deal with an action principle, which are the fundamental equations that dictate how a system evolves. Sometimes these equations are invariant under a conformal transformation, which is basically a mathematical operation that scales the metric tensor.
This is the conformal shrinking atom framework. This absolutely melted my brain.
It's a fun one.
Because mathematically, you can apply a transformation that completely halts the expansion of the FLRW metric. You set the scale factor, a of 2, to a constant. Space is now rigidly static.
A fixed coordinate grid where the proper distance between galaxies never ever changes.
Right. But to ensure that the actual observed physics remains identical, to explain why distant galaxies look dimmer and why their light is redshifted, the conformal transformation applies the time-dependent scaling to the masses and sizes of the physical objects themselves.
Yes. Under this dual mathematical framework, the space between the galaxies is static, but every quantum mechanical bound system, every hydrogen atom, every star, every planet, and the very physical rulers we use to measure distance are systematically and continuously shrinking over cosmic time. Mass increases and physical dimensions contract.
So the universe isn't growing, we're just getting smaller.
Correct.
The void between the Milky Way and Andromeda is a fixed, unyielding distance. But because the atoms in our measuring sticks are shrinking, it takes progressively more of our tiny rulers to cross that gap. So from our perspective, we perceive the gap as expanding.
It is a flawless mathematical duality. The ratios of the measurements remain completely invariant. There is no physical experiment you could ever perform to prove whether the metric space is expanding or if the atoms in your instruments are shrinking. The observational consequences are indistinguishable.
And it gets even deeper when we look at the emergent space model, drawing from holographic principles and black hole thermodynamics.
In the standard FLRW model, space is treated as a fundamental base-level background. But in emergent models fueled by the ADS-CFT correspondence and entanglement entropy, space is not fundamental at all.
It is a macroscopic illusion, like temperature. A single atom doesn't possess a temperature. Temperature is an emergent property that only exists when you have billions of atoms interacting.
Precisely. In emergent frameworks, the dimensions of space we perceive are generated by the quantum entanglement of underlying non-spatial degrees of freedom residing on a boundary surface. The metric expansion of the universe isn't a stretching of a pre-existing fabric. It is the continuous thermodynamic manufacturing of new space.
Space is literally being computed into existence out of quantum information. The universe is evolving toward a maximal entropy state, a de Sitter vacuum, by generating more spatial volume.
It's a profound shift in perspective.
So what does this all mean? We have mathematically rigorous models where space is an expanding geometric metric, where redshift is just kinematic Doppler shifts between freely falling observers, where the universe is completely static but atoms are shrinking, and where space doesn't even fundamentally exist, but it's just a holographic projection of quantum entanglement.
It means that human intuition is merely a localized evolutionary tool. Our desire to picture a physical thing happening, a balloon stretching, a river flowing, is just our brain desperately trying to map tensor calculus onto primate experiences.
That's a great way to put it.
The mathematics simply describe relationships, ratios, the flow of information over time. Whether you visualize an expanding metric, drifting galaxies, shrinking rulers, or emergent holograms, the profound underlying physical reality, the equations themselves, remain perfectly intact, endlessly predictive, and deeply elegant.
It is profoundly humbling. And, in the quiet of the night, incredibly peaceful. You realize you aren't being dragged by some invisible cosmic fabric. You are just resting in your local static space-time, while the global coordinates softly re-index themselves around you.
Reindexing coordinates.
Oh,
Very poetic.
as we begin to bring this deep dive back down to Earth, I want to leave you with one final, gentle reminder. If this kind of rigorous atmospheric unraveling of the cosmos brings you peace, if it helps quiet the noise of the day by zooming your perspective out to the absolute grandest scales imaginable, please take a moment to subscribe to the YouTube channel Decoding the Dark. Like their video, and let it be a companion for your quietest, most contemplative moments.
It's well worth your time.
We've covered immense ground today. We've seen that the universe wasn't a violent bomb exploding into a pre-existing void, but a boundless, self-contained manifold undergoing a kinematic evolution of its internal metric. We've learned that local systems, our bodies, our Earth, our solar system, are perfectly safe, governed by local static metrics, completely ignoring the overcrushing expansion.
We've explored the dark voids of Kotler holes, the topological ghosts of a toroidal universe, and the mind-bending reality that our expanding cosmos might just be a mathematical mirror for our own shrinking existence.
As you stand under that canopy of crushed diamonds on a clear, moonless night, I want to leave you with a final thought to mull over. A thought regarding the absolute limits of our reality.
The horizons.
We often talk about the particle horizon, the absolute edge of the observable universe, roughly 46 billion light years away, defined by the maximum distance light could have possibly traveled since the Big Bang. We look at that horizon and think, that is our universe.
But there is another horizon, one that is much closer and much more absolute.
The reachable universe. Because the expansion of the universe is accelerating, driven by the cosmological constant of dark energy, the metric distance between us and distant galaxies is increasing at a rate that is exponentially compounding. Because of this, if we launched a spacecraft from Earth today, traveling at the absolute maximum speed limit of space-time, the speed of light itself, we could only ever reach galaxies that are currently within 16 billion light years of us.
The acceleration acts as a cosmic event horizon, constantly drawing closer.
Exactly. Every single galaxy, every star, every world beyond that 16 billion light year mark is forever physically unreachable. Even if we had infinite time and infinite energy and moved at the speed of light, the space between us is being generated faster than we could ever cross it. They're slipping quietly past our cosmic event horizon, like ships disappearing into an impossibly dense fog, never to return and never to be touched.
It's a sobering reality of the math.
It is a beautifully melancholic, soothing thought. The universe is unfathomably vast, but our cosmic neighborhood is fundamentally physically limited. We are standing in that open field, gazing up, and the quietest, most monumental migration in the history of physics is happening right above us. Thank you for exploring the dark with us. Keep looking up and let the quiet of the cosmos wash over you.